So, good evening, everyone. Let's get started after a little bit of, let's call it technical difficulties, getting audio working. So, last week we left off after getting our rendering working. We have this nice, wonderful little triangle spinning on our screen, which is wonderful. So, what you might remember from last time is I spent about 25 minutes working on our transform matrices, finding out that they were sort of in the wrong order. They were row major order, we needed column major order, and a lot of time actually calculating the projection matrix, and I've kind of decided that we should probably try to avoid those kind of problems. So the first task today is that we are going to switch out the manual generation of these matrices with a library called GLM, which is OpenGL Mathematics. So it looks kind of like this. So this is a wonderful library for doing sort of matrix transforms and vectors for OpenGL. And I've gone ahead and installed it ahead of time so that we don't have to work on that. So what we're going to do is we're going to try and first of all switch these matrices out one by one with the equivalent GLM code. These three matrices are projection, view, and model matrices. We'll switch them out with actual with the GLM functions, appropriate GLM functions. And once we've got that running, we are going to try and sort of abstract away the idea of a camera so that we can control a camera, and we're going to go and see if we can't get some input and see if we can't move the camera based on user input. So that's sort of the first plan of the day. So let's get nice and simply started. So the first one, the nasty one, is the projection matrix. So we're going to start with that one. So first things first is we're going to have to include a little bit of the different libraries. So GLM. So today I can apparently spell include, but I can't put angle brackets. That's going to be interesting. Has a class for 4x4 matrices. It has a lot of classes for various matrices. We want the 4x4 one. So doing that, we can get a, rather than doing this nasty bit of code, we can say we need a GLM matrix 4, which is the 4x4 matrix. Then we can make our projection matrix. And instead of calculating all of this by hand, GLM has a nice handy function to do a perspective transform, which we need to include first. So to do this, we go GLM, CTC, matrix, transform, HPP. This is like a header library with a million different types of transformation matrices you can get, including the perspective matrix that we're interested in. So, like I was talking about last time, it's based on the same principle as this. We just don't have to sort of write it out. So we give the field of view in the y-axis to it in radians, which is what we are already calculating it as. Then we give the aspect ratio. Then it needs the near and far clipping planes. So Z near and Z far. And rather than doing all of this math on our own, we'll just let GLM handle it and hope that that goes well. Of course, this is not likely to compile at this time because we can't just load the 4x4 matrix directly. So, the question then becomes, how do we take this wonderful 4x4 matrix, get the internal representation, and pass that to OpenGL? And For some reason, they're matrix functions is what I want, I think. Apparently not. So as you're probably noticing, I'm sort of browsing the documentation because it's wonderfully, wonderfully simple, of course. So, types. We have a map 4 here. So this is going to be the fun part where we apparently decide to look at the code, which is surprisingly uninformative. The alternative is we try and let C-line guess. So here, it's not one of the operators we need, nor is it the length. I vaguely remember having seen this somewhere. Oh yeah, this is also something I noticed. We have sort of noise extensions, including simplex noise, which when we get as far as doing stuff like level generation, this is going to be really, really useful to have. But that's a whole nother matter. So there's like this GLM value pointer that you call on the actual matrix. Cool. So GLM value pointer of this, and complaining that it can't resolve the issue, probably because we need another include. Yay! GLM, UTC, and this one's called type pointer. So let's try compiling, and that links. So now we should refresh and we should get the same thing. Yay! So that's sort of the idea. The magic of GLM is that you can sort of get away with simple stuff like this. So we're going to go ahead and try and replace these other two, which are simple translation and rotation matrices. So the model matrix here is a simple rotation around the z-axis. So that means what we do is we go for a map 4 model matrix. Here we can do GLM rotate. And so the idea is, in this case, you start with an existing matrix and then you rotate that. So we're just going to start with an identity matrix, and you can construct an identity matrix by just making a map 4 and then just giving it a constant 1 floating point. Supposedly, at least. Then we want to give it the rotation amount, and this again is radians, so we're just going to copy the same rotation. And we're going to be rotating around the z-axis, so we want to make a GLM vector 4, which is going to note our rotation axis. So we rotate around the z-axis, and for that we just want to include Yet another thing. Mood. CLM. Vec. 4. Okay. Complaining about it? No complaints. Great. So that should sort of do it for the model matrix. Again, we need to get this value pointer from the matrix like this. And okay. So apparently it's not a 4-dimensional vector, it's a 3-dimensional vector. We only give it the x, y, and z. So we'll try that instead. And it built successfully. So let's take a look at the program. We're again, no change at all, which is what we're looking for. We're just hoping to make life easier on ourselves. So the view matrix is a little bit more interesting because we have both a translation and a rotation involved here, and we have to get these in the right order. So the idea here is that again, we're modeling this as we have our camera, and then we're moving the world relative to that. So in this case, what we're doing is we're starting by, let's see if I get this right. We start by rotating the world, this time around the y-axis, and then we translate the world after that. So what we do is we just reassign it the same. Then we have a wonderful little translate function here, which takes an initial vector we want to work on, and then we can translate it by some amount. And what we're doing is we're translating it 3 vector minus 2 in the z direction. So if everything goes well, this should be completely equivalent, and we've now gotten rid of, well, at least one of the most common errors, at least for me. So yeah, that seems to work. And if we just rerun it, yeah, I got the order of that wrong. So for those in doubt, what's happening right now is that the camera is moving and then rotating. So what we want to do is we want to switch these two around. So we translate and then rotate. So let's translate first and then rotate. So normally when we get a little bit further along, this is probably what we're going to want to do, rotate first and then translate. Probably, maybe. We'll find out. So let's just compile that and see how that works. So, yeah, now nothing works. This is my favorite situation. Oh, wait, of course. I'm just being obtuse as usual. So, reason is we need to start with that identity matrix and then modify that afterwards. There we go. That still looks a little bit on the weird side. It's not important. Not at this point. So what we want to do now is we want to try and sort of factor this a little bit out, because right now we have in the middle of our render, we're setting up our camera position, and that's a little bit weird. So what we're going to do is we're going to sort of factor this out. So let's create a class for this, camera, And we'll get it. So this camera class, we are gonna start with a constructor as per usual. And then what we want to do is we want to have but we're going to want to include the GLM library here, because we're going to want to have access to the 4x4 matrix again. So we want a function that will return a 4x4 matrix, which is the current sort of camera transform. So that's both the perspective and the view transform rolled into one. And for the camera internally, we want to store a 3-dimensional vector, which is our position in the world. And then we are going to store a 3-dimensional vector of rotations, which is going to be sort of a pitch, yaw, and roll thing. You usually get away with just pitch and yaw, but it's nice having rolls sometimes. So we're going to add rotation, and these are sort of going to be the two main things we're going to have. Yeah. So what we'd like to do is we'd like to have the renderer, when it renders, rather than taking a delta, which it shouldn't care about what time it is for rendering, we're going to have it take a camera. Of course, we're going to want to include that so that it knows about, we're going to want to include that here. So you'll notice this is a constant reference. That means that when we're declaring the interface over here, we don't need to have the camera class declared. We can just say, well, there is some class called camera. You don't need to worry your little head about what it is. That makes dependency tracking for the compiler a little bit easier, which is always a good thing. So we're not going to care about time or anything like that. We're not going to care about a lot of these matrices. The model matrix is still sort of the property of the renderer, because this is all about where the object is in time. We're just going to give it the identity matrix for now, so it'll just be floating in the middle of nowhere. Instead, we're then gonna say we're gonna have sort of a GLM mat, which is we're gonna call it camera matrix, which will ask the cam for its transform, and it's gonna complain about that because we're using a constant reference. We're gonna have to tell it that this doesn't change the camera in any way. And then rather than having both a view transform and a projection transform, we're just going to have a camera transform. I might regret this at some point, but this is what we're doing right now. So if we head over to our vertex shader, it now only needs single combined camera transform here, and that should do it for the camera. So we need to implement some of this stuff at some point. One thing we will, however, do here is we're going to have, at 4, we're going to have the perspective projection transform already pre-computed, because that doesn't change very often, so it pays off to have that lying around. And it's the one that involves division and all sorts of other nasty stuff. So we're going to pre-compute that. Great. So let's try and implement some of this. So for our camera, when we instantiate it, we are going to want to calculate our projection transform. We are going to use, we have to grab the code from over here, because we already have it ready. We're gonna, as usual, start by hard coding stuff, and it'll become sort of more dynamic later. At least that's the plan. So our field of view on the y-axis is, I think we set it to something like 60 degrees. Yeah, 60 degrees. So GLM has its own nice way of accessing the value of pi, where I can also tell it what sort of position I want. So I want to do that. My aspect is 16 in floats divided by 9 float. That's just for good measure. So set near is 0.1 float, and set far, we're still going with 10 float just to start somewhere. Right, so that pre-calculates our projection transform. And let's just start by sort of default initializing our position and our... No, I don't want a t-vector, I want a vector. I might want to sort of include that over here. So we're going to start by initializing a 3 vector here. So our initial position is going to be 0x, 0y, and then we're going to move a little bit back, back on the y-axis. So that means the camera is at 2, which is backwards on the y-axis. Don't ask why. Because, yeah, it has something to do with whether your coordinate system is left-handed or right-handed, and that's just a decision people made. So as far as rotations are concerned, we're just gonna have no rotation initially. Great. So in order to grab, we need the transform here. So to calculate this transform, what we are going to do is we are going to start with we're going to start by, and this is where it might go really, really wrong. It depends a little bit on, let's just take a look at the documentation, because that might actually help a little bit. Because the trick is, when you're doing these kinds of rotations, whether you are adding, or whether you're sort of left side multiplying or right side multiplying the resulting rotation matrix onto the existing matrix. Because if it's multiplying it on the right hand side, then we can just start with the projection matrix. If it's on the left side, we have to start with an identity matrix. So that's sort of the question. And there's really, look at ortho, lots of weird stuff, rotate. Yay, no description. But I'm pretty sure that's, if it's meant to be sort of a replacement for the OpenGL 3.0 and earlier versions, then it's going to be multiplying on the right side. So that means we start our transform with our projection transform. So we take a copy of that. Then from here, we are going to want to, first of all, translate. So we take our transform, and then we do a GLM translate. We start with the initial transform, and we translate by our position. Then we're going to go through the rotations individually. GLM rotate. So we're going to want to rotate our transform so far. The angle is going to be based on our position, and then we're going to, or the rotation, and the rotation around the x-axis. And then we're going to say that, yeah, this is, by the way, rotation around the x-axis. And I like writing STD apparently because that should not be standard, that's GLM. Then we do the same for the other three axes. So for Y and for Z. So rotation around Y-axis here, and rotation around the Z-axis. And I'm a little bit quick on the copy-paste apparently. And then we return this transform. So this should basically, I was thinking of, yeah, of course we still need to create a camera here in our main loop here. So to do this, we're gonna have to include our camera, and I like to keep these somewhat alphabetical. So we're gonna include the camera. So rather than doing, we're just gonna make this really, really simple where we just have a camera here and make that, and let's see what happens. We fail miserably because I've uncommented a little bit more than I need to, or than I should. So let's try it with that. So far so good. Let's refresh. Yay! Nothing. So that typically, again, indicates that we've done something wrong. And in this case, I'm pretty sure the problem is that we should... How long have you guys been unable to see the code? And why has nobody said anything? So in this case, we're probably moving ourselves the wrong way because of this wonderfully inverted thing when you're dealing with the camera. Yeah, that helped a lot. So we really don't want to think about that, so hopefully we can just negate that. It has a function for that. Great. So that seems to be working.